Okay, I'm ready.
The year is 2125. An artificial signal is received from deep space. Upon analysis from the European Southern Observatory, it was discovered that the narrow-band signal originated from the direction of Messier 87 and persists for exactly 7.4 seconds. Its structure is unintelligible at first, but when processed through a quantum computing system, the signal resolves into a sequence: 5009, 5011, and 5021, and so on, which the computer quickly realizes that it's a sequence of prime numbers. And so it begins. More primes follow.
You meet an alien species. They come to Earth. Do you know about prime numbers? They don't know the language. They think about what do you mean by this word prime? You start tapping out like 2 taps, 3 taps, 5 taps. You do that. The alien species has done like any thinking at all. They'll be like, I got such a natural sequence.
That's right. Prime numbers are not culturally defined. They are mathematically fundamental, divisible only by 1 and themselves. And so any intelligent system with access to basic arithmetic would eventually identify them.
And that's where we are. We've taken off the headset. There's these obelisks sitting there smiling at us. Quiet.
I mean, if alien life with no shared history, biology, or context uses the same mathematical constructs, doesn't that imply that mathematics is universal? And what about the notion that math was thought of as a human invention, created to solve specific problems on Earth? I mean, that's exactly how it was used. People assigned numbers to objects, like 1 sheep, then 2, 3, and all the way to 48. But now imagine what happens when the objects disappear. If there are no sheep, no herd, no context, and no observer to count, my question to you is 48 an objective fact embedded in our reality? Or does it only emerge when intelligence is present to define it? And so, if 2 hypothetical intelligences recognize the same concept of prime numbers, what does that lead to in our understanding of modern physics? Early mathematics had no abstraction. Numbers were attached to physical things. There was no concept of 2 in isolation, only 2 goats, 2 baskets, and 2 bricks. In ancient Babylonia, astronomers calculated lunar cycles using base 60 arithmetic. Their goal wasn't to understand the cosmos. They needed calendars for agriculture and civil planning. In ancient Egypt, geometry was developed to remeasure farmland lost by the Nile's floods. It wasn't until later that abstraction emerged. Greek mathematicians introduced formal proof and deductive reasoning. Indian scholars developed zero and positional notation, and these all became fundamental to the mathematics we use today. But here's the million-dollar question. If math started as a human tool, why does it work so well in describing nature? Why do tools designed to measure grain quantities end up describing planetary orbits, quantum behavior, or black holes in modern science? I mean, if math was made for Earth, then why does it describe the universe at the same time?
Mathematics allows us to take all of the complexity of the universe and wrap it up neatly into an equation or a system of equations that we can then understand and model.
If we can trace the history of big ideas in math, like how base 60 arithmetic came from ancient Babylonia, and geometry was developed in ancient Egypt, then why not trace our own history? Like, have you ever wondered that your great-great-grandparents were connected to Queen Elizabeth, King Henry, or Albert Einstein? So the question is, how? And this is why we've partnered with MyHeritage for this video. It is the world's #1 leading platform for discovering your family history. It can help you discover more about who you are and where you come from. MyHeritage makes it fun and really easy to use. Just start your family tree by adding yourself, your brother, or any other family member's information. The more details you provide, the better it gets, and it truly has the potential to help you find new relatives. And let me tell you, what I found was really surprising. Through their Instant Discoveries feature, I learned that my great-grandfather, born in 1901, worked as a farmer and settler on June 6, 1947, and I found this out from an old Australian newspaper. But that wasn't all. I uncovered my great-grandmother's immigration record, showing her traveling to Detroit, Michigan for a 2-day visit, accompanied by my great-great-grandfather. I also came across an old photograph showing one of my family members discussing machines and electricity with the Indonesian president at the time. With their AI features, You can enhance the image, turn it into color, and even animate it to bring it to life. MyHeritage made this whole process incredibly simple. They give you access to over 36 billion historical documents. So if you've ever been curious about where you come from or who your ancestors really were, this is your chance. Start your journey today with a 14-day free trial. Just click the link on the screen or scan the QR code here and begin exploring your family history with MyHeritage. So now let's get back to the video. If you're skeptical about the claim that math reveals something deeper, let's look at a practical case. The first one is E, Euler's number. Might look like just another constant. But let me tell you this, if you put 10 chocolates into 10 boxes at random, what are the chances that one of them ends up in the correct box? Surprisingly, that probability is very close to 1 over E, 36.79%. This isn't how E was originally derived. The constant comes from calculus and exponential growth. The probability connection came much later. Now let's look at the next number, pi. This one is different because it was discovered through empirical observation. Around 2,000 years ago, Babylonian mathematicians estimated pi using the circumference of a hexagon inscribed in a circle. Later on, during Archimedes' time, he used more refined polygons to approximate pi more accurately. He kept increasing the number of sides, getting closer and closer to a circle, essentially doing calculus logic centuries before it was formalized. And we fast forward to 16th century Europe, and we get the invention of the imaginary number I, the square root of -1. It was so bizarre that people at the time thought the number existed only outside the realm of tangible reality. So why even bother thinking about it, let alone inventing it? Well, it turns out, through robust mathematical derivation, that if we take all these E, pi, and I, they form this beautiful equation. E to the power of pi I plus 1 equals 0. The Euler's identity.
I mean, one of the things that people often look to in beauty is the simplicity. So if you look at E equals MC squared, so when a few concepts come together, that's why the Euler identity is often considered the most beautiful equation in mathematics.
In 1604, Galileo performed an experiment that demonstrated that the universe follows mathematical laws. He designed an apparatus that showed this clearly. So here's what happened. He wanted to find the relationship between distance and time, so he used a ramp, a ball, and some form of time measurement. He used arbitrary units, like 1 Galileo, 2 Galileo, 3 Galileo, and so on. The distance the ball traveled in 1 Galileo was recorded as 1 unit. So we've gone 1 unit of time, 1 unit of distance. Now, if he tried 2 units of time, the ball didn't travel twice the distance, it traveled 4 units. So he thought this relationship is not linear. Then he tried 3 units of time and got 9 units of distance. So at that point, it became clear. The distance the ball travels is directly proportional to the square of the time. The relationship between distance and time was mathematical. And it holds up. And this part really blew my mind. You can test this experiment anywhere, on a hill, on Mount Everest, on Mars, or on the moon. The result remains just as valid today.
If necessary, at the end, to translate what you figured out into English, into the world, into the blocks of copper and glass that you're going to do the experiments with to find out whether the consequences are true.
So in other words, we'd expect math to be so precise in describing the physical world, because sometimes it's the generalization of what is happening. And our physical reality is just a special case of this generalization, where we are constrained to a certain degree with something.
I think people often find it puzzling that something abstract like mathematics could really describe reality as we understand it. The best you can do is to describe some mathematical structure. You say there are things that satisfy the Dirac equation or something like that, which you can't understand what that means without mathematics.
That's exactly what happens with Einstein in the general theory of relativity. He wanted to come up with an unconventional idea that gravity isn't a force, but the curvature of space and time itself. So he needed to expand the matrix. Einstein realized that Newton's laws couldn't explain how gravity works in accelerating frames, or under extreme conditions, like near a black hole. So he needed a new framework. But these equations appeared to not exist in physics yet, although they were already prevalent in math. And that's where Bernhard Riemann comes in. He gave a famous lecture in 1854, called On the Hypotheses Which Lie at the Foundations of Geometry, where he proposed that space could be curved, which, if you ask me, was an idea way ahead of his time. Riemann developed the metric and curvature tensor. The very structure he had envisioned turned out to be exactly what Einstein needed. And in 1915, Einstein finally published the general theory of relativity. It remains one of the most beautiful examples of mathematics predicting physics long before the theory existed.
If you say, I have a three-dimensional space, ordinary space, I want to talk about ordinary space, three-dimensional space, and you begin to ask them about theorems. Then they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. And later on, it always turns out that the poor physicist has to come back and says, excuse me, when you wanted to tell me about the 4th dimension.
It's clear that mathematics operates in the abstract, and through that abstraction, it allows us to describe hidden structures that help us understand the world. So let's walk through an example. This next bit was adapted from a famous TED Talk by mathematician Roger Antonsen. I highly recommend watching the full presentation of his. Anyway, we start with a two-dimensional shape, 4 triangles arranged in a 4-3 pattern. Now let's fold them together to create a 3-dimensional object. The result is a square pyramid. And let's just take 2 of these square pyramids and join them. That way we get a new shape called an octahedron, which is one of the 5 Platonic solids. And you might recognize it from our previous video featuring Professor Donald Hoffman. We'll return to that in a moment. Now, once we have this shape, we can rotate it along different axes and observe it from various angles. And each time, it looks slightly different, even though it's the same geometrical object, because what we're seeing here are the 2D projections of a 3D structure. This is the same principle we explored in the constrained hyperspace video last year. And we can do it one more time, and the more perspectives we explore, the more we learn. Each shift reveals something new about the same underlying object, just because we change our perspective.
I can use this as a tool for creating understanding. I can take 2 of these and just put them together like this and see what happens. And it looks a little bit like the octahedron. Have a look at it. If I spin it around like this, what happens? Well, if you take 2 of these, join them together and spin it around, there's your octahedron. Again, a beautiful structure. If you lay it out flat on the floor, this is the octahedron. This is the graph structure of an octahedron.
Let's pause here for a second. Remember this structure? It closely resembles the geometric forms proposed by Don Hoffman, the ones he suggests exist outside of space-time. In his concept, these forms represent a kind of consciousness that is more fundamental than space-time itself. They exist beyond our perceptual reach and are silently staring at us.
Geometric structures, not a dynamics, just sitting there. Here I am. Could be millions of dimensions, it could be trillions of dimensions.
So you might be wondering, how do 2 different researchers, each exploring the nature of reality through mathematics, arrive at similar shapes and structures? One is using math to examine perspective and dimensionality, while the other is using it to describe consciousness as a pre-space-time entity. This overlap is too difficult to ignore. It's exactly identical to what we discussed at the beginning of this video, the hypothetical discovery 2125, where future humans detect a prime number sequence sent by an extraterrestrial civilization, a civilization with no shared language with us on planet Earth, no common sensory frame, and no shared numerical concept, yet somehow conveying something familiar that is mathematics. Here's my own realization while writing the script for this episode. Mathematics may not just describe the universe. It may be the substrate it runs on, and more specifically, in this universe, everything that exists and follows the same physical laws seems to align with the same underlying mathematical structure. That's why our math appears consistent, even across different minds. And so throwing the same apparatus, like Galileo's device before, this time on planet Kepler 16b, would essentially yield the same equations. Assuming the same physical laws apply to both systems,
Let's have a mathematically precise theory of consciousness that starts as simple as possible. And then we have to boot up what we call space-time and the physical world as conscious experiences within conscious agents that they're using as an interface, a simplifying interface to help them interact with other conscious agents.
Roger Penrose, in his 1989 book, The Emperor's New Mind, argued that no machine could replicate human consciousness. This view runs counter to the ordinary beliefs at the time. Marvin Minsky, who many figures regard as the father of artificial intelligence, claimed that the brain is just a computer made of meat. What Penrose described was that it's not about how complex these machines are, or how fast they are, but rather that they were fundamentally limited by algorithmic logic. And that is something that human thought appears to bypass. And so, in order to fully explain this, Roger Penrose turned to quantum physics. He proposed that consciousness might arise from non-deterministic quantum-level processes, the kind of computation that goes beyond neural architectures. It wasn't long until Penrose collaborated with Stuart Hameroff. He introduced the idea that quantum coherence might occur inside the brain's microtubules. This is cylindrical protein structures within neurons. Their purpose is to regulate the shape and division of cells. But in this context, Hameroff believed they might also serve as biological quantum devices, the perfect candidates for sustaining quantum coherence. So together, Penrose and Hameroff proposed the orchestrated objective reduction theory. According to this, consciousness arises from orchestrated collapses of quantum states within these microtubules. Each collapse, or reduction, is not just a physical event, but a discrete moment of conscious experience, and they are internally driven by thresholds of gravitational self-energy.
That's what the brain does. That's what the microtubules do. Orchestrates the objective reduction. Hence the theory is orchestrated objective reduction.
Physicist Max Tegmark dismissed this idea on physical grounds. He argued that quantum coherence in a biological environment like the brain would decohere in less than 10 to the minus 13 seconds, far too quickly to have any cognitive relevance. Tegmark's conclusion was that if the brain were using quantum processes, we'd need to be thinking 10 trillion thoughts per second for it to matter. But despite this, in 2013, experimental results from a Japanese team detected vibrations in microtubules. If quantum activity could persist in microtubules for longer durations, then the biological conditions for Roger's theory might be plausible after all. This concept also touches on the debate around free will. Classical neuroscience suggests determinism, that all thoughts and decisions are caused by prior brain states. Roger Penrose challenges this claim. He argues that quantum indeterminacy could introduce genuine unpredictability into neural processes and disrupt strict causal chains, not through randomness, but through non-computable structure. This would create space for choices that are neither deterministic nor algorithmic. Okay, it seems that I've been talking a lot of gibberish English, but what does this all mean? How do you make sense of this piece of information? Well, the bigger consequence of this idea is that consciousness is not merely a byproduct of physical law. It may be fundamental to the existence of the universe itself. In Roger Penrose's words, somehow our consciousness is the reason the universe is here. It's almost the same message as Donald Hoffman, who also thought that what is fundamental is consciousness, although his idea is a little bit different in terms of how he explains the link to the physical world.
My assumption is that the fundamental reality is just consciousness. When we have different, for example, spaces and times, one organism has 10 dimensions of color perception, another one has 4, we have 3. Some organisms see in 4 dimensions or 2 dimensions.
If consciousness depends on quantum laws, and quantum behavior follows mathematical structure, then awareness itself may be grounded in mathematics. So if that's the case, then mathematics is not just a language we use to describe the universe. It may be the operating system the universe runs on. And what if we extend this thought process even further? What if there's an idea that describes not only that mathematics is the operating system, but that the very fact that our universe is mathematical? And so we're going to explore this in the last chapter of this video. Physicist Eugene Wigner once published an article, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The statement pointed to a genuine epistemological puzzle. Why is it that equations invented by humans to solve local problems end up predicting phenomena far outside their original domain? This question is really the core hypothesis of Max Tegmark. He proposes what he calls the mathematical universe hypothesis, the idea that the universe is mathematics, not merely described by math, but made of it. In his view, every structure that exists physically corresponds to a mathematical structure.
I mean in plain English that our universe doesn't just have some mathematical properties, but that it fundamentally has only mathematical properties.
And this is the reason for the bit we showcased at the beginning of this video. A prime number remains prime, whether observed by a human, an alien, or an algorithm, because math at its core does not depend on language or culture. If it can be defined by relations, symmetries, and axioms, then it is a candidate for physical existence. And so, this view extends the legacy of Plato's mathematical realism. The mathematical forms in Plato's ontology, like perfect circles, numbers, geometric solids, exist in a timeless and non-physical realm. They are not invented, but discovered by conscious beings. What Max Tegmark hypothesizes is something more radical, that the Platonic realm and physical reality are the same thing. Our universe is not embedded in math. It is math.
The reason math has been so effective in describing the world is that the world is mathematical, completely mathematical. We actually inhabit a mathematical structure. The approximations we've found so far are just some simpler math approximating, the actual math.
And so constants of nature like the fine structure constant, gravitational or Planck's constant, are not set by anything. They are intrinsic properties of the mathematical structure we happen to inhabit. And what we call physical laws are just features of that structure. But remember, it's only the reality we inhabit, not anywhere else. Only the space-time we know and love. And so if there's another structure or reality out there, this might not be the case. The Galileo experiment we showcased earlier might not yield the same relationship. Perhaps it could be another variable that is not time squared. Or the prime number would be another concept entirely. And all of this subset of mathematical structures would be classified into the level 4 multiverse by Max Tegmark, where it encompasses every single one of these subsets. And our reality now is just one point in an infinite mathematical landscape. So if Tegmark is correct, then consciousness, particles, space-time, and all physical phenomena are emergent aspects of the underlying math. The brain is a mathematical object, the observer is a mathematical process, and existence itself is formal, not material. It's a position that pushes the boundary of what science can empirically address, that maybe the simplest explanation is that our physical reality is mathematics in motion. Astrophysicists are sexy. Don't forget to click the link in the description box or scan the QR code to begin exploring your family history with MyHeritage.